Hi, today we're going to talk about homogeneous coordinates. As described in chapter 12 of the Coxeter book. Some of our goals today is going to be to introduce the basic concepts of the homogeneous coordinates and verify some of the axioms. We're going to prove several theorems analytically, and we're going to discuss the interpretation of this coordinate system as far as what it means for our projective geometry. We won't necessarily cover this in this order. So to begin with, we have already established that we have a point with capital X, and then it can lie incident on a line with lowercase x. So the basic idea of this coordinate system is we're going to, for each one of these objects, assign a triad of numbers. We're going to swap to lowercase x's or lowercase variable names for the points. We'll switch to capital for the lines. The lines will be in brackets, and the points are going to be in parentheses. Other than that, there's not a lot that's special about what's going on with these three numbers. They're just three numbers, such that they're not all zero. And we're also going to establish that this point is equivalent to this point here. So if we scale all three numbers in the triad by the same number and they remain proportional, then this point is going to be equivalent to the original point. And the same thing with lines. Once we've established that, if we're talking about generic points, we can reduce this down to just a single x, knowing that this is going to be three different values that we might call capital X. And then this would be three values that we would call lowercase x. Objects of opposite type are going to be said to be incident if and only if their inner product is zero. So here we have line x, point x. We're going to say that they are incident if we can establish that the inner product of little x dot big X is going to be the same as little x dot big, that should be big X dot little x. And the inner product, the dot product is going to be the same dot product we learned from linear algebra. And if that equals zero, then we can say that this point and this line are going to be incident. We're going to find that there's several different tools from linear algebra that's going to work out well for us in trying to work with these coordinates analytically. Another tool from linear algebra was the determinant. And we can establish that points x, y, and z, they're going to be all three collinear if and only if we expand all 3 points, put it in a matrix, and find the determinant of that matrix. If there's zero, then all 3 points are going to be collinear, which is just an extension of this inner product, trying to find it simultaneously is equivalent to finding the determinant. With that in mind, if the determinant is zero, then we know that there's something about these 3 points that makes them dependent, literally dependent, which means we could find this third point as some linear combination of the first two. So for instance, if I talked about point X and point Y on the same line, if I was to take all their coordinates and add them together, then I'd get some point that's going to be on that same line. If we add them, that's going to give us some point in between. If we do X minus Y, we're going to have some point that's going to be to the the extreme beyond X. If we do Y minus X, then we'll have some point extreme of Y. We can scale these with some with some coefficients, and that's going to shift where it's going to fit on that line between X and Y, or relative to X and Y. If I want to find out what the join and the intersection of objects are, we're going to use the cross product. So for instance, if I want to know what the triad for this line that contains X and Y, I just need to do the cross product. So the three values of this line is just going to be whatever the result of X cross Y is going to be. And it's going to be equivalent if we do the dual. If I want to find the intersection of these two lines, it's going to be at a point that's determined by the cross product of these three values crossed with these three values. And this actually gives us enough information that we can actually start trying to look at things analytically. So for instance, we could look at Pappus's theorem, which says if we have 3 points on a line, A, B, C, if we have 3 points on a different line, E, F, G, all three distinct, we can form a hexagon with alternating sides. So from A to F, F to C, back over to E, down to B, G, back to A. If we take those alternating sides and we find the intersection of those sides, those intersections are going to lie on some line here in red. So to do this analytically, we need to first kind of reframe this in terms of our coordinates. So we're going to simplify, since these are arbitrary points, we're going to simplify E as E1, comma E2, comma E3 in parentheses. But since these are all arbitrary numbers, we'll just say E1, or excuse me, little lowercase e in parentheses, and then F and G and so forth. So we can change our picture to look like this. And since these two points are collinear with G, we can find G by doing some combination of E and F. Same thing with C, it's just going to be some combination of A and B. Then to find the side that connects A and F, then we were just going to cross A with F. If I want us to find the side that crosses connects E and B, then it's just going to be E cross B. If I want to do this side here, that's going to be F cross A plus B. And we can continue that along and identify all 6 sides of the hexagon, which will look like this. Now if we want to, and I guess these need to be in parentheses. Let's try adding them and then we're crossing them. if we want to find these 3 points, then we need to then find the incidence of this green side and this green side. Those will be the opposite sides. And so we're just going to take this triad, whatever it ends up being, and crossing it with this triad here, and that will give us the coordinates for this red point here. And we could do the same for the other 2 points, which is going to look like this. Then to confirm that those 3 points are indeed collinear, we want to expand them. We'd have the 3 points for this, the 3 values for this point, 3 points for this point, 3 values for this point, put them in a matrix as we did before, find the determinant, and verify that it's 0. Problem with this is this becomes really computationally difficult really quickly. We've already kind of got these really complicated looking points. This is the triad for some point. This just represents 3 numbers, and it's going to be a little bit difficult to find. In fact, I created a Maple program that calculated this out. So I started off with 3 points, or excuse me, 6 points, just as I labeled them here. They're going to be represented by a vector, which is just a list, which is all we've established so far. And each one's going to be established by a point A is going to be a list of A's, B is going to be a list of B's, C is going to be the combination of A and B, E and F are going to be a list of E's and F's, and G is going to be some combination of E and F. And then here I crossed each of those points in the appropriate way and got 6 new sides. These are the alternating sides of the hexagon. And then I took these and crossed them in the appropriate way and got those 3 points. Put them in the matrix as described. And this whole thing represents the matrix of those 3 points. So imagine having to do that by hands. Luckily, we have technology, and sure enough, the determinant when you plug that all in is 0. Now, if we want to do this regularly, we're going to want to try and find some simpler version of dealing with this analytical coordinate system. So we need to learn a little bit more to try and cut down on this type of really gross computation. To do that, we're going to begin talking about the axioms and verify that those work, and that's going to give us some insights. It's going to make us make sure that this really does work for the axioms and the axiomatic geometry we've been working with. But this is also going to help us have some insights on how we can maybe streamline some of this process. The first 2 axioms, 213 and 311, they say that if I have 2 distinct points, they're going to be incident with just 1 line, and 2 lines are going to be incident with just 1 point. If you look back, we were able to establish this line using some computation, which means there's only 1 line that we can identify given any 2 points. Likewise, if I have 2 points, their intersection is going to be established by some computation, the cross product, which means there is only 1 value, 1 triple of numbers that we can establish that's going to represent the intersection of those 2 points. Which means that definition of incidence confirms these first 2 axioms. To get axiom 312 and 217, 312 says that if we have 4, or that there exists 4 points of which no 3 are collinear. so quadrangle. To do this, if we want 3 of those points to be non-collinear, then we just need to make sure that the determinant is not 0. If it's not 0, then they're not going to be collinear. We don't know much else about them, but they're not going to be lying on the same line. And that's an easy enough thing to do. So we can confirm that there are 3 points that are not collinear. So that gives us 312. And then to do 3 diagonal points of a quadrangle are not going to be collinear. We're going to draw ourselves a quadrangle where the first 3 points, PQR, are going to be non-collinear. So here's my determinant. And I've established that the determinant for these 3 points is not going to be 0. So these 3 points at least are not collinear. And so we have a quadrangle. I want to establish A to be the intersection of QR and PS. Now I've established what P, Q, and R are. It's just going to be some triple of P, 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 Q, 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 R, R, R. But we haven't established what S is. So the first thing, excuse me, we need to try and do is establish where S is. Let A be the intersection of PR and PS. Well, that's going to mean that A has to be some combination of Q and R. And then since S is on the line P in A, or line PA, then S has to be some combination of A, which is Q and R, plus P. So then we have that S is just P plus Q plus R. Then we want to establish where B is. B is going to be the intersection of PR and QS. It's on the line that contains Q and S, and it contains P and R. So that means, and it's in between, so that means we're going to find the difference, and we're going to have P plus Q plus R minus Q. So point B is going to be P plus R. And then point C, it's going to be some combination of P and Q. So C is going to equal P plus Q. And then to verify our axiom, we want to show that points A, B, and C are not collinear. And so to do that, we do what we've done before. We're going to set up a matrix with the triples of the 3 points listed, and then try and show that the determinant is not 0. If it's not 0, then the points are not collinear. So here's that matrix. This is A, this is B, this is C. And we've established that A is just Q plus R, B is just R plus B, and that C is P plus Q. And because of the way we have a Q on the front, we have a Q on the back, we have an R on the front, we have an R on the back, which means that much of this is going to cancel out, and it turns out that this determinant is just this determinant. And we've already established that it's not equal to 0. So that means that these 3 points are not going to be collinear. And since Q, R, and S, well, mainly just P, Q, and R, are completely arbitrary, that tells us that for any A, B, and C, it's not going to be collinear. And we can use this approach. So we've verified the first 4 axioms, and we can use this approach to actually help us try and prove Descartes' theorem analytically. So here is a setup for this Descartes' theorem, which just says that if I have 3 non-collinear points that are concurrent with a single point that I'm calling U, and the first points are going to be P, Q, and R, and they are projective with 3 other non-collinear points, P prime, Q prime, and R prime, then we have 2 triangles, and the sides of those 2 triangles are going to intersect at points that are all collinear. So to prove this analytically, we're going to first, just right off the bat, establish that R lies on this line that has R and U. So that means it's going to be some combination of R and U. And Q prime is going to be similarly some combination of Q and U. And P prime is going to be some combination of P plus U. Now this side here contains this point here. But this point is also on this line here. So this point has to be some combination of R and P, but it also has to be some combination of R plus U and P plus U. Did I get that right? Yeah. Well, this doesn't have any P's, or this doesn't have any U's. This line does not pass through U, so it can't have any U's. But this one does. So to get these U's to cancel, I'm going to switch these and do it like that. One of these is going to be have to be negative, so then the U's will cancel. So we're going to make this one negative, scalar by a negative scalar, and it's the difference. Then the U's will cancel, which tells us that this point here is going to be P minus R. Similarly, this point is going to be P and P, PQ. This is going to be P minus Q. I guess I actually had that right before. It should be R minus Q. And then this point is going to be Q minus R. And then we're going to expand these 3 points, just like we've done a couple times, and put it into the matrix and determine whether the determinant is 0. And here's our matrix. And sure enough, the determinant will be 0. If we work this out computationally, Q1 minus R1 times this block times the determinant of that block, minus what, Q2 minus R2 of this second block, the determinant of that block, and then plus Q3 minus R3, and that would give us this block, and then add that up and we would get that it's 0. So indeed, these 3 points are going to be all on one line. So that gives us those 4 points, or 4 axioms. For the 5th one, we're going to exploit the fact that if everything's on the same line, then their inner product's going to be 0. So if I have a projectivity that relates these 3 points, that means they're going to be incident, which means these 3 values are going to be 0. And if I want to choose that it's, and if I want to verify that it's true for any point that has this same relationship, then it's going to have the same same scalar for some value that shifts it around, whether we're on the line or we're projected to the point. Line projected to the point. Or the point projected to the line. And if we work this out, x times x, and then we're going to have x, y times lambda, and then we're going to have plus y x lambda, and then we'll have y lambda squared. This square just means we're going to project forward and backwards, but we know that this is going to be 0 because this is already established to be 0. We've established this is 0. This is the original 3 points in our projectivity. And then these 2 parts, they may not be individually 0, but they're going to cancel each other out. So this is going to be 0. So for any point, if we have 3 points that are invariant, then the other 3 points are going to be invariant as well. And we can actually use that to then analytically prove the fundamental theorem as well. Now, what exactly does this mean in terms of our actual projective geometry beyond this system works? It's convenient for us because there's no parallel lines that we would need for the Cartesian coordinates. So we've eliminated the need for that. And these homogeneous coordinates work well with our sense of duality. But what does this actually mean in terms of the actual geometry? And in particular, the projection. What these 3 numbers are representing is actually 3 points in 3-dimensional space. So if I have a point in the projective plane, that actually represents a line that's passing through in 3-dimensional space with the equation x plus y plus z equals 0. And our coordinates actually represent all the points along this line, because remember, we were allowed to scale them up and down. If we fix one of these 3 values so that it's a single, if we scale these values for all the points and all the lines in our plane so that one of the numbers is a fixed value for everything, then what we've done is established a plane, projective plane, and establish all the points and lines on that plane. If the scaled version of this point misses misses the plane, then we would consider that to be one of our points or lines at infinity, which we're happy to deal with inside of our projective geometry. There's obviously a lot more to the sense of what these coordinates can allow us to do and their applications, beyond just proving theorems. But that is about all the time I have for today. Thank you for your time, and enjoy the rest of your day.